Okay, already on to yet another chapter. So after doing general second-order linear equations, last chapter, this time we're doing wave equation. So one-dimensional version. And I've already picked out the problems for this chapter, which, let's see. We'll be doing this chapter all next week. Now, I think the problems we do, actually better check.
Before spring break?
What?
After?
March 9th.
Right, yeah.
That's the Wednesday before spring break.
Yes.
Yeah.
And then we start chapter 5, but we won't finish chapter 5 until after spring break. So of course after this, you won't have any homework due for quite a while. Okay.
But then this homework is due on Monday, which is
How bad is it?
it's quite it's doable. I don't know if it's doable by Monday. But
Okay.
it's doable in general.
Okay.
It's doable
Well, might be fun enough because when I gave Simon this similar material in 417, that was one of the lighter ones, but maybe it wasn't true this time. But, so, of course, that assignment was messed up because the book got all the problems wrong in the back. Okay. Well, yeah, because I haven't heard. Well, actually, until a few minutes ago, I heard nothing about this latest batch of problems. So, well, okay. How about? All right, we'll make the chapter 3 homework due Wednesday instead of Monday. So hopefully I'll have that a little bit because it is a bit soon, even though the chapter was short. But okay, and then. I won't say anything about chapter 4 yet. I mean, I'm prepared to postpone. If there's any postponement at all, we'll put that after spring break. But chapter 5 won't be due for a zillion years anyway, so because it won't even be done with the chapter then. So, okay. That's an interesting question, actually. I don't know. It might kind of fall off the edge, but yeah. Yeah, I wouldn't be surprised if no. Because also, what if we don't really get through the chapter? What if we fall behind from chapter 7? So there will definitely be a homework on 7, but I don't know. Could make it a bonus in case anybody needs it or something like that. So yeah.
That's welcome.
Okay. Good to know. So this one-D wave equation is the u dt minus c squared whose x is 0, where c is a constant. So the general form of second-order linear equations, like we had last time, if we let the notation a would be 1. B would be 0 because there's no utx term, and then capital C would be equal to minus little c squared. So the discriminant b squared minus big A big C is just going to be little c squared. It's positive, so this equation is hyperbolic. That means we're going to have two sets of characteristic curves. Which results in a finite propagation speed. So first I want to say a little bit about how the equation is derived. Okay, so what we have is a problem of a vibrating string. Okay, and in this case, solution u, that xt represents the displacement from equilibrium. Okay. So how much the string has been plucked at any particular point x and any time t. Okay. So what we have is Newton's second law, which as you probably know is force equals mass times acceleration. What we get is following. Okay. And we're applying the second law on a particular interval, subset of this string ranging from some point x to x plus delta x. So, so along the entire segment, we have UTT, second derivative with respect to time. That's your acceleration. And then rho is the density. And this is a one-dimensional object, so we have density times length. In one dimension, density times, or whatever dimension, density times size gives you what?
Mass.
Mass. Yeah, so we normally think of it as mass is density times volume, but we're in 1D, so it's density times length. Okay, so this is your mass times acceleration part. And on the right side, you're going to have whatever forces. Now, there are several forces that I could include that would lead to extra terms in this equation, and all of that's in the notes. But I'll just focus on the one that's of interest to us, and that is, for the equation we're going to solve, we have the tension in the string, and then we have udx at the right end of the segment minus udx at the left end. Okay. All right. Now, so what we do is we go ahead and divide through by delta x, and we also divide through by rho, and we let delta x go to 0. So what we have, so on the right side, or sorry, the left side, we're just going to have UTT. On the left side, we're going to have t over rho, and then here we have du dx at a point minus du dx at another point over delta x, and that's delta x goes to 0. It's definition of derivative, but we already have a derivative. So in this difference quotient, we're going to converge to the second derivative. This tension over density is a constant, and of course it's a positive constant. And we're going to refer to that throughout. Because it's positive, we'll call it c squared, just to reinforce that it is positive. And that gets us out of having to write square roots all over the place when we come up with a solution. Okay. And this equation, commonly known as the wave equation, but it's also known as the telegraph equation. Okay. So what it describes is transverse vibration. Displacement up and down, as opposed to longitudinal vibration that's from left to right. Okay. Now, what we need, because it's second order with respect to time, need two initial conditions. So the solution at time 0 is some given function f of x. The time derivative, du dt, at time 0 is some other function g of x. So we have to take both into account to describe our solution. Okay. Now, a little more about what's happening physically, where this tension term comes from is so the net force that's being exerted on this segment of the string is due to the tension is T sine theta 2 minus T sine theta 1. Where, and I'll draw, it'll be easier to draw what's happening. If here's your string, and here's the point x, and here's the point x plus delta x. So theta 1 and theta 2, okay, not gonna have much of an angle here. So the angle here, theta 2, so theta 1, theta 2 are the angles that the string makes with the positive x-axis. Okay. So if I make this triangle a little bigger, then we can use right triangle trigonometry. Sine theta 1, and similar for sine theta 2, is going to be, of course, opposite over hypotenuse. Now, we want to try to approximate that, at least, because we're assuming that delta x can be arbitrarily small. Now, here's our opposite side, right here. And what that is that's a change in u. That's a difference in position between, so this height of the string and this height. So this amount of displacement is delta u. You can think of it that way. The hypotenuse is this side here, or this side here for this triangle. And if I'm willing to fudge a little bit, and this is not a bad approximation in the case where displacements are small and delta x is small, the hypotenuse is roughly change in x. So that's how we get that these sine terms, these sine factors up here, become du dx's down here. So it's a little bit of right triangle trigonometry and some assumptions about small displacements that lead us to approximate the net force due to the tension by first derivative with respect to x. And then letting delta x goes to 0 causes this wave equation to fall out. Okay. All right. Any questions about that derivation? Okay. Now, there are other applications of a wave equation that comes up quite often. For instance, it can be used to model sound waves. Although what's interesting is with sound waves,
Longitudinal waves, right?
yeah, it's longitudinal. For sound waves. So you end up getting similar equations from different physical considerations, but the same derivatives pop out. Okay.
Won't they be orthogonal?
What?
Their propagation is orthogonal, right? This goes from up and down. The other goes with-
Yeah, for a vibrating string, yes, it's up and down. But if you're when you're instead modeling or propagation of sound waves,
where will it be different?
what's happening is you have propagation of, like, for instance, suppose you have sound waves going through one-dimensional medium, so it's propagation along the x-axis. So it's longitudinal vibration in that case. And what happens is, or for instance, if you're modeling a vibration through a rod, so it's longitudinal vibration through each piece of a rod. In that case, the constant here refers to a Young's modulus of whatever medium you have. Okay. Let's see. Electric current through a wire can also be modeled through the wave equation. So really, any kind of wave. That's why the name is so general that this comes out. So it's not just for vibrating string. You go to 2 dimensions, 3 dimensions, like for instance, 2 dimensions, ripples in a pond can be modeled using a wave equation. So ocean waves, when you're talking about a 3-dimensional case. Okay. So what we're going to do today is focus on how do we come up with a solution of the wave equation. And we can actually use what we were doing recently with canonical forms to get a solution more easily than you might expect. And at least this particular equation has a pretty simple canonical form. Oh, don't want to drop that. So we have a well-known solution formula for the wave equation in this case. So a Lambert solution. Okay. So the problem we're going to solve, a specific problem, is kind of what we have been solving lately. All the way back to the Cauchy problem. So UTT equals c squared uxx on the whole real line, and deposit t, and then we have these initial conditions. Okay. So what we do is, similar to the techniques we've been dealing with from the last chapter, if we were trying to get this in the canonical form, because we just have this one constant coefficient that works out fairly nicely, that your change of variables, and this is what you would get if you applied the techniques of the last chapter. This is why also we're using c squared. Your characteristic variables are x plus ct and x minus ct. And if you go ahead and compute all the partial derivatives that you need, so for instance, ux is equal to uxc plus u eta, and du dt is cu c minus cu eta. Okay. And then you have, applying this twice, formulas for uxx in terms of second partial derivatives with respect to c and eta. Minus 2c squared u, this is u squiggly squiggly, the first derivative, or first term rather, c squared u eta eta. Okay, so after you incorporate all of these, so really we just have these derivatives here that we plug into there, and what happens is just about everything cancels out. And all that you're left with is u c eta is 0. So this is expected because that is a canonical form for hyperbolic equations. But you only have, that's your only second derivative term. You actually get a like a 4c squared UXC eta equals 0, but then you can just divide through by 4c squared. And you left the equation in this form. And I brought this specific equation up last time, in fact, with today's class in mind, because we now know how to solve this. So this is equal to some function of eta plus some other function of c. So we just have to figure out what those are going to be. Now, another way to think of it then is u of xt is going to be phi of x minus ct plus psi of x plus ct. Okay. So now we just have to figure out what are these functions, and the way we're going to do that is using the initial conditions. Okay. So we'll go ahead and substitute t equals 0 in here, and we'll also take the time derivative and set t equals 0, and see what we get. Oh, also unpleasant. Hopefully it's still, yeah. Okay, so from the initial conditions, so we go to our general solution to set t equals 0. So we have u of x0, which is going to be 5x plus psi of x. That has to equal f of x. And then du dt at x0. Well, we take so we're going to have phi prime at x minus ct, but
That's an x.
what?
It's t 0, right?
Yeah, it's going to turn out to be just x. But then from a chain rule, we have x minus ct, so that's going to give us a factor of minus c right here. And then for the second term, similar idea, we have psi prime at x plus ct, but t is 0, so that's going to give us x. And then you take a derivative of x plus ct with respect to t, and you get c, and that has to equal g of x. Okay. So any questions about how that came about? It's just chain rule.
I'm just slow.
Okay. All right. So what we'd like to be able to do is treat this as, because we have two equations, two unknowns, phi and psi. So this would be able to treat it like any other system of two linear equations, except for one thing. In the first equation, we have phi and psi. Second equation, we have phi prime and psi prime. So what should we do so that both equations have the same entities that we're solving for? Yeah, we'll go ahead and integrate. So we'll have minus c, and we'll have an antiderivative. So I'm just going to integrate from some lower limit x naught, doesn't really matter what it is, to x. And we'll have, okay, actually, not over here. I'll have, this is just going to be phi plus c psi. Alright, so they're integrating a derivative. Over here, you're going to have an antiderivative of g. And then, so we'll call it generic antiderivative with x as a upper limit, some constant x naught as a lower limit. And the reason I'm writing it this way is, normally I might have like a arbitrary constant of integration in here. But basically what I'm doing is I'm picking out a specific antiderivative of the left and right side. I don't really care which antiderivative, just a specific one. So we have some unspecified lower limit x naught in here. Okay, so now if I take this equation and this first one up here together, now I have a system of two linear equations and two unknowns, phi and psi, which I can write in matrix vector form. So I have my unknowns, phi and psi, and then on the right side I'll have f, and then I'll have the antiderivative of g. And then my matrix will just be the coefficients of these. So for the first row, my coefficients will be 1 and 1. And then down below, I'll have the coefficients minus c and c. So now I can just invert this matrix. So I can say 5x psi x is equal to 1, 1 minus c, c inverse times f and antiderivative of g. Okay. Now, inverting this is no problem. The determinant is c plus c, so 2c. So I'm going to have 1 over 2c, and then swap diagonal entries, negate the off-diagonal entries. Okay. So now I can go ahead and carry out this matrix vector multiplication. So the first row is going to give me phi, second row is going to give me psi. So I'm going to have 5x is going to be c over 2c times f. So that's just going to give me 1/2 f. And then minus 1 over 2c times the antiderivative of g. Okay. And then the second row is going to give me psi, so I can go ahead and write that out in similar fashion. So that's going to give me c over 2c, so 1/2 f. And then we just have plus. Okay. Any questions on that? So now we have phi and psi. We can go back to our general solution that I have on the previous board and express all of that in terms of f and g. Okay, now I deliberately left this general solution here, because now I'm just going to plug my psi and phi into that. So, okay, so for phi we have 1/2 f, but now we're plugging in x minus ct into phi, so we have that. And then plus, or minus rather, over 2c integral from x naught to x minus ct g thus.
They would cancel then eventually.
Sort of. Well, it depends on what cancels though.
Oh, but it's x plus ct. It's not the
Yeah.
same interval.
Yeah.
Right.
Okay, so this is phi of x minus ct. And then I add on psi of x plus ct. So that's going to give me 1/2 fx plus ct plus integral. Yeah, the limits of the integral are different. They will not cancel. In fact, they add together in a nice way because
Bottom line to the top.
yeah, because what I can do here is I can flip the limits of this integral as long as I change the sign. And then the integrals chain together, going from x minus ct to x naught, from x naught to x plus ct. So now I can cut out the middleman x naught and make that one integral. And then the f terms I can combine. So that's f of x plus ct plus f of x minus ct, and then this integral from x minus ct to x plus ct to g. Okay, so this is a limited solution to the one-dimensional wave equation, the Cauchy problem. Any questions on how we got that? Okay. All right. Now, so let's take a look at this solution in some simple cases of interest that can give you an idea of how the more general solutions behave. Okay. Now, so what's interesting is this term right here, you're taking f of x and causing it to propagate to the left, because this is x plus ct is a shift to the left. And then here, taking your initial data f of x and it's propagating to the right. And the speed in both cases is the same, c. So you can see why we used utt is equal to c squared uxx, because otherwise we'd have square root of c throughout this formula. That'd be kind of a pain. So we have two-way propagation, same initial data, spreading out to the left and right. And at any particular point, you're just averaging those two displacements. So what's happening is, at any particular point, x naught, t naught, for this part of the solution, what's happening is, to see how the solution behaves here, you'll backtrack along this line. So this is x naught minus c t naught. So this is a line with slope 1 over c. And also in the other direction, this line has slope minus 1 over c to x naught plus ct naught. And you're going to see what was f of x equal to at these 2 points, and you average them. And that gives you at least this part of the solution at that point x naught, t naught. So it's taking certain pieces from initial data. Which pieces? You use these characteristic curves to figure out where your data is coming from. All right. So let's see what that means for this initial data. Suppose we have, let's let f of x be equal to 1 for x between minus 1 and 1, and 0 otherwise. And let's let g of x be 0, just so we can focus on how this part of the solution behaves. And then after that, we'll do the opposite. Okay. Now, so how the solution behaves is, okay. If I mark 1 and -1, so it's in here where our initial data is non-zero. And from here we have these characteristic lines. Okay. So this line is x plus ct is -1. This is x plus ct is equal to 1. This line is x minus ct is -1. And this is x minus ct is equal to 1. Okay. So in here we have initial data that's equal to 1 being propagated to the left and the right. So because of a 1/2 here, in these regions, I'll try shading them. So where you only have one of these two regions and they're non-overlapping, I'll shade them differently. So where they're not overlapping, you're only going to get one of these two displacements. So here you get the displacement to the left, x plus ct. Here you only get displacement to the right, propagation to the right, x minus ct. So because the initial data was 1, in this region, the solution is equal to constant 1/2. Here also it's equal to 1/2. Now, just to make clear here, this is the xt plane that we're looking at. Now, in this region, the propagating waves overlap. So you have both of these displacements. So here the solution is equal to 1. So what's the solution equal to anywhere else?
0.
Yeah, because out here, the initial data hasn't propagated to this part of the real number line yet. It will later in time, because these waves are going to keep propagating to the left and right. So at any particular point x, eventually this initial data will get to you. But until then, if you're down here at x that's far away from your non-zero initial data, and only a short amount of time, let's mark these u equals. Anywhere else, the solution is 0. Where have I not labeled yet?
That
So
small
little
triangle.
crisscross.
Yeah, up above here. So in between the two regions, also the solution is 0. And the reason for that is, at this point in time, the initial data has moved on from you. So it's carried too far to the left here, too far to the right. So basically, so think of it this way. You think of initial data as being like a little bitty train has two cars. One car starts moving to the left, one car starts moving to the right as soon as t becomes positive. So here you're on one car, here you're on the other car. Here you have to wait for a train to arrive. Here you missed it. So if you want, you can look at it that way. Okay.
So on those parts, you get one car here, one car there, but in that small triangle, you get both cars.
Here? Yeah, you can pick what car you're on, I guess.
Right.
Yeah.
I mean, yeah.
And actually, if you have a train that's
Okay.
split in two that's moving into opposite directions, and you miss both cars, it's kind of sad. But okay. So any questions about the behavior of a solution in this case? Okay, now let's look at the opposite case, where f is 0 and g is this, we call it a characteristic function, which is an unfortunate choice of notation in this class because characteristic has already been used for other things. But in general, a characteristic function is a function that is equal to 1 on a certain interval and 0 elsewhere. So in this case, because you have no initial displacement, but your initial velocity is non-zero, then you get very different behavior. And once again, we need the characteristic curves to figure out what the behavior should be. Okay. So now let f of x be 0 and g of x is 1, and x is 3 minus 1 and 1 and 0 otherwise. Okay. Now, so once again we look at the xt plane. Okay. I can say from my last diagram that the vertical line I drew was definitely not the t-axis because I had both minus 1 and 1 to the right of it. Okay, so I'll draw a proper t-axis this time. Okay, so here we have minus 1 and 1. We have the same characteristic lines. Okay, so we have x plus ct equals minus 1, x plus ct equals 1, x minus ct is minus 1, x minus ct equals 1. So what you can do to see how solutions are supposed to behave, you have the same regions as before. So this region, that one, the part where we overlap, the part in between them, and then anywhere else. Okay. Now, so the parts that are outside of any region, it's easy enough to conclude that u is going to be 0, because what happens is your solution this time, which I have formula for, is 1 over 2c times the integral of x minus ct to x plus ct of g of s ds. So it's that interval, x minus ct to x plus ct, that you're concerned about. So for instance, if you are here, then you're going to backtrack along the lines that have the same slope. So here is x minus ct and x plus ct. And you're going to integrate g along this line segment. But g is equal to 0 on the entire segment, so you're not going to get anything. All right. Let's take a look at a point in here where the regions overlap. So you're going to have, again, x minus ct, x plus ct. Now what's happening in this case is, okay, my picture is not that great. Okay, a little better. So what's going to happen now is you're integrating the function 1 from x minus ct to x plus ct. Notice both of your limits of integration are within the interval where you have non-zero data. So here, anywhere in here, the solution is equal to the integral of x minus ct to x plus ct of 1. Because on your entire characteristic triangle, if you will, so if you draw any point xt up here and take the characteristic lines back down to the x-axis, that forms a triangle. And actually, this is going to come up in later sections, so I'm going to name it now. And this is a triangle that has vertices xt, x minus ct and 0, x plus ct and 0. So when I say characteristic triangle, that's what I mean. So we can figure out how the entire solution behaves by putting a point xt anywhere in here and looking at what's happening on the characteristic triangle. And how is the initial data behaving on the base of the characteristic triangle. So, let me just separate this. Okay. So, in this region where we have the overlap, x minus ct to x plus ct is entirely within the region where the data is equal to 1. So, I'm just integrating 1. But that's just going to be the difference of the limits.
CT.
No. What's the difference of the limits? It's not ct.
Wait,
2 CT.
This and this.
2 CT, right?
yeah.
Yeah.
What he said.
Okay.
I didn't hear the
Two
question the
C.
first time, so.
Over 2 C gives it just T.
Yeah. So, okay. So wherever two overlap, the solution is just equal to t. So the solution starts increasing in value as you get to this point. Now, let's take a look in here, between the two regions. Now, in the previous case, the solution turned out to be 0. But that's not going to be true this time. So if I draw characteristic lines,
So
Yeah.
the solution in that bigger triangle will be 1 and the smaller triangle will be T?
no, the solution
In the entire...
in this entire overlap. So let's see, where this strip and this strip overlap, it's t. So whatever the t coordinate is, that's the solution throughout that overlap.
So what did we draw the little triangle for?
I picked a sample point to give you an idea of how a solution is going to behave, but it's an arbitrary point within this overlap.
So it has to be T.
Okay.
Okay. Because if I pick any point in a triangle, I'm going to pick up the whole interval, x minus ct to x plus ct. Okay. Now, over here, I do the same thing. Now I have a much bigger characteristic triangle. And I'm going to integrate from here to here. So this point now is, I'm going to erase this previous characteristic triangle. You have it in your notes, but it's causing my picture to get way too cluttered. Okay. Now, this is my x minus ct way out here. Here's my x plus ct out here. I'm going to integrate g. Wow, this picture is awful. In terms of my characteristic slopes. Let me fix that.
Can you use a yardstick like they do in elementary school?
If we had one here, yeah. Okay. So I'm integrating from -1 to 1. But I'm only going to pick up the part where g is not 0. But the thing is, when I'm way up here, my characteristic triangle is larger, the base is larger. I'm picking up the whole interval -1 to 1. So in here, and I'll do different shading so you can see which region I'm talking about, between the two strips, my solution u is equal to the integral 1 over 2c integral of g. But what now it's always this. But now if I fill in where g is equal to 1, what interval will that be? So I'm starting at this point, I'm looking at the base of my characteristic triangle, but I just want the part where g is non-zero.
Maybe 1 to 1.
Yeah, because now the entire interval where I have g non-zero, minus 1 to 1, is contained within the base of a characteristic triangle. So now is this integral I'm going to evaluate, and what I'm going to get this time?
1 over c.
Yeah, 1 over c. So what's interesting is down here, the solution is increasing in value, but up here, it's equal to a constant. Now, it's strange. So now here is where it switches from one to the other, which happens to be at x equals 0, but then we have this t value right here. So from u equals t to u equals 1 over c, the switch happens at, so that common vertex happens at x equals 0. And what about t? Well, t, it's where these two lines intersect. So we have intersection of x plus ct equals minus 1 and x minus ct is equal to 1. And a common t value. Now, if you added these equations together, you get 2x equals 0. But we already can see from a picture that x equals 0. So I'm just going to drop those. So now, if you subtract the equations, then you have 2ct is equal to, oh, wait, I'm sorry, I messed up. X plus ct is equal to 1. Yeah. And x minus ct equals minus 1. I knew I had something backwards. Okay, so 2ct is equal to 2, so it means that t is equal to 1 over c, which is kind of what you'd expect, because you'd expect the solution to be continuous. I mean, g is a piecewise constant function. G is discontinuities, but when you integrate that kind of function, the integral is still going to be continuous. So t starts from 0, it's increasing, and then when t hits 1 over c, it switches to this regime, and it remains at 1 over c, at least in here. Okay. Now, what we have not accounted for, oh sheesh, are within these individual strips. So once again, we deal with a characteristic triangle. So if I pick a point here, for instance, and I do it with a characteristic triangle, I go down to here, so this is my x minus ct, and over here, the x plus ct. So now, I pick up part of the interval, because here's my base of my characteristic triangle. I pick up a part starting from minus 1 and going up to x plus ct. So what I could say is between the lines, x plus ct equals plus or minus 1. So between this line and not in the overlap, my solution is 1 over 2c integral. So now I'm picking up, okay, so from here to here, so from minus 1 to x plus ct of 1. So now I can just work that out. So that's just going to be x plus ct plus 1 over 2c. So that's what my solution looks like in that case. And if you checked, you would see that that matched up continuously with the other behavior regions. So for instance, once you hit this line, x plus ct equals minus 1, well, x plus ct equals minus 1, so you would get 0. And then in the other region, the other strip that's heading to the right, x minus ct equals plus or minus 1. You're in here, so you do a characteristic triangle, and your solution, you're picking up a different part of the interval, starting from x minus ct up to 1. So you get 1 minus x plus ct all over 2c. All right, so you use the same approach in all cases. You pick a point in whatever region of interest, look at your characteristic triangle, mark the points x minus ct and x plus ct, and you see where does the base of your characteristic triangle overlap with where your initial data is non-zero, that interval minus 1 to 1 in this case. That tells you, that intersection between the two tells you where you integrate over. And then you can just work out, at least you're integrating 1, so the integral is easy to work out. Okay, so now I'll just finish labeling here. Okay, so this is u is equal to 1 plus x plus ct over 2c. And over here we have 1 minus x plus ct over 2c. Here's 1 over c. Here, the overlap u is equal to t, and then elsewhere it's equal to 0. I know that's quite a mess.
I feel like I'm in geometry class.
Yeah, I can see that. Okay. Any questions about that big old mess? Okay. Hopefully I get through the last bit in the last 12 minutes each. Okay. The last thing I'll talk about is, suppose you're not solving a problem on the entire real line, but half of it, like just the positive x-axis. And at x equals 0, you have a boundary condition. You actually get some interesting behavior in that case. Okay, so a semi-infinite string. Okay, so same equation, but now we have same initial conditions, except x goes from 0 to infinity. And our boundary condition in this case will let u of 0 t equals 0. You may have a different boundary condition. This is Dirichlet, because we're specifying u. If you have like du dx of 0 t equals 0, you can use the same approach as what I'm going to show. Obviously, things will turn out differently. Now, solving this, you have the exact same situation as before when you have your canonical form. So u of xt is, okay. If you just use a Lembert's solution formula, you get the, what you had before, f of x plus ct plus f of x minus ct, and then this integral. Actually, for now I'm going to leave the two integrals separate, because we have to tinker with one of them. Now, here's the problem. We cannot use this solution as is, because x plus ct, if x and t are both positive, x plus ct is going to be positive. But x minus ct might be negative. So, the thing is, you're only given initial data, f and g, on the positive x-axis. You're not allowed to evaluate f or g at any point where they're negative. So, so this solution is only valid if x is greater than or if x is greater than ct. So for x greater than ct, then you, okay, actually, yeah, for x greater than ct, go ahead and use a regular solution formula. There's no problem there. So here's what we do. Okay. And actually, I'll say greater equals ct for convenience, assuming that f and g are at least defined at 0. Okay. So if x is less than ct, you use a boundary condition. Because your solution is equal to, as before, 5x minus ct plus psi of x plus ct, from using the canonical form. So now I plug in x equals 0. So I get phi of minus ct plus psi of plus ct. And from the boundary condition, that's supposed to be 0. This gives me a relationship between phi and psi. So now I can say that phi of minus ct is minus psi of ct. So alternatively, I can say phi of x is equal to minus psi of minus x. Just by replacing ct with minus ct with x throughout. So, okay. Now the thing is, psi we computed before. Psi of x is 1/2 f of x plus 1/2c integral of g. So now I can define phi in terms of psi. So phi of x is minus 1/2 f of minus x minus 1/2c integral from x naught to minus x. Okay. All right. So now what I can do is use this for my general solution formula. Just might get this done in time. Okay. Now my general solution formula is phi of x minus ct plus psi of x plus ct. But now that's equal to minus psi of ct minus x. So because the x gets negated. So now I can write out everything, and what I get is 1/2 f of x plus ct minus f of ct minus x. So that comes from that part of psi, and then I have plus. 1/2c, and I'm going to get the integral from over here. From the first term, I'm going to get, actually, I'm going to flip the limits. So it's ct minus x to x naught of g plus 1 over 2c integral from x naught to x plus ct of g. Okay, so so these two terms come from minus psi of minus x minus ct, which is just ct minus x. Okay, and I flipped the limits in the meantime. So just like before, the integrals can be combined. So that's equal to 1 over 2c integral from ct minus x to x minus ct, or x plus ct of g. And this is a formula that you use for x less than ct. So if you're sufficiently close to the x, to x equals 0 of t-axis, depending on what t is, you have to switch formulas. Okay. So that's what you have in that case. And then I've already written on the previous board, for x greater than or equal to ct, just use the solution formula we had before. So the last thing I'll mention is how does this solution behave? So, so here in my xt plane, okay. So I have some point xt, and I want to know what the solution is like at that point. How's it pulling from initial data? Now, what I used to do is draw my characteristic lines, my characteristic triangle. So this is x plus ct and x minus ct. And what would happen before, like for f, it would pull half a value of f from here and half a value of f from here. But now, x minus ct is negative. So I reflect that over here, and I have ct minus x, which is now positive. So now it is pulling from a value of f right here. So it's like it's bouncing off the t-axis. And also look at the formula. So here's adding this half displacement, and then it's subtracting this one. So it's taking negative a value from here. But the point is, because it's we're choosing to pull the initial data from, we see reflection. So if you actually observed the behavior of a solution over time, for instance, let's suppose you had f only being non-zero out here. You have propagation to the right, propagation to the left. You have it propagating to the left, it bumps into the t-axis, it flips, and it starts propagating back again. So your boundary conditions can be really change how the solution behaves, and that's important for whatever you're modeling, that you use appropriate boundary conditions. Because what if, for example, and this is a key aspect in numerical methods, suppose you're trying to simulate wave propagation on a large domain, but practically you have to cut it off somewhere, like a finite domain. You don't want to use, you may not want to use Dirichlet conditions if you're going to have your waves bouncing back at you. That's not physical, because you really mean the waves for waves to go far off into infinity or minus infinity and never come back. Now, if you have periodic boundary conditions, that could be a problem, because what could be happening in that case is your waves go out one end and come back around the other end. Also, probably not physical. So, what some people use are absorbing boundary conditions, which are pretty hard to implement, where you have a wave coming in at your boundary, and you have to make a boundary basically suck the wave up. So it doesn't reflect, it doesn't come back around the other side, and that simulates proper physical behavior. So there's a lot of work done on coming up with appropriate boundary conditions so that you're simulating on a domain that is virtually infinite, but of course you have to make it finite for your simulation, and you choose boundary conditions that preserve that physical behavior. So it's,
So the waves that are going right are going right.
yeah,
The ones that are going left are reflected upon reaching that.
yeah, in this case with this boundary condition,
This one.
which might not be what you want. So, but if you don't want that, yeah, there are ways around it, but it's not an easy thing to deal with. Okay.
Is that bad? Like, how is that bad if they reflect?
If there's reflection,
Yeah.
well, because then you're getting a solution that doesn't reflect what you're physically simulating. So it's not valid when compared against the actual conditions that you built your model on. So when you're setting up, a lot of times you're developing your PDEs based on physical laws, but then you have to look at what's really happening physically on your domain. Are there boundary conditions? How do you account for them? Because because what we're seeing here is it drastically changes the behavior of a solution. Okay. Well, I'm out of time anyway. So. Okay.